Hi, welcome to this lecture on priority queues. My name is Dr. Ritesh Ajula. So what is a priority queue abstract data type? A priority queue just stores a collection of entries. These entries can be key value pairs, and the key is typically a real number or an integer, and the value is typically an object. It can be an object from the monster class, an object from the animal class, whichever object from whichever class. These are your values. The key is associated to the value. So we can think of these two things as being one unit inside the priority queue. The key also indicates the priority for this particular object. So perhaps one object is more important than another. You can associate the importance with respect to the object with this notion of a key. So what makes it a priority queue is, sure, we can store these collection of entries, these key value pairs, but what makes it a priority queue is the ability to extract the maximum key or the maximum or the minimum key, and the complexity of this differs. The complexity differs with respect to the way we organize the priority queue. We can organize it in different ways. We can have an unsorted list to represent the priority queue, a sorted list to represent the priority queue. But the way we choose to represent the priority queue determines the complexity of extracting the minimum key and the maximum key. And remember, the key is associated with the value. So if we extract the minimum key, then we are extracting the minimum key with the value itself, or the maximum key with the value itself. So that's what makes it a priority queue. So having said that, we have five functions or methods that we can use as the minimum for the priority queue. We can insert entries into this list, this priority queue, and for that you just have to give the object with the key value. So in other words, insert with the argument e for entry. And then we can remove the minimum. If we remove the minimum, we're returning the entry with the minimum key. All right, here it says removes the entry with the smallest key. Alternatively, we could also remove max. And if we remove max, we'll be removing the entry with the largest key. Additional methods that we can find in our priority queues can be just to see what the min is. This doesn't remove the min, it just returns the min. We also have methods to see if the priority queue is empty, that is, if it doesn't have any entries inside of it, and also how many entries is housed in this priority queue. That gives us the size. And in terms of applications, we can think of, well, you can think of many applications, I'm sure. But the three in this example is standby flyers, so people who need to be prioritized with respect to boarding a plane, or often when planes overbook, we can put priority based on who paid the most to get onto the plane. We can assign priority to participants of an auction based on how much they are willing to pay for an item. And of course, we can obviously associate priority in the stock market with respect to share prices and so on. So there's a lot of applications of this, and I'm sure you can think of many more applications of priority queues. It comes up in most problems where we want to assign, where we don't want all of our entries to have the same associated key value, but rather a distribution based on their priority. So let's talk a bit more about the key values that are associated with the objects. So the keys in a priority queue can be arbitrary objects. They themselves can be objects in which an order is defined. So if they are objects, we need to define some kind of ordering that allows us to associate these keys. So remember I said that a key could be a real number or an integer. Well, then that's easy, right? You can relate different integers based on the less than and equals to sign. You can say 2 is greater than 1. 3 is less than 5. That's fantastic. There's a way of arranging our keys in the set of integers or in the set of real numbers. That's important. So if you are going to be defining your keys as objects, you need to have some kind of relation, some kind of mathematical relation to be able to say this object is greater than the one object or it comes before another. So the way we can do this is by using this mathematical notion called the total order relation. And the total order relation has three properties. The first is the reflexive property, which means that a value is equal to itself. This is the reflexive property. Then you get the anti-symmetric property. This is a combination of the symmetric and asymmetric property, which says that if you have a relation between x and y and the relation between y and x, the same relation, that means that x is equal to y. And finally, we get the transitive property, which states that if you have a relation between x and y and a relation between y and z, that means that there exists a relation between the same relation between x and z. This is important. If you want to have your keys to be objects, we need to make sure that these objects adhere to these three properties. We already have these properties, the notion of a less than or equal to, this notion of less than or equal to for integers. We've got it for real numbers. But if you want to define your own objects, you would have to define this relation as well. And once you do that, you can use those as your keys for your priority queue. In this course, we will not be looking at, we won't be looking too much at representing objects using these kind of sophisticated relations, but rather I will give you things like integers or real numbers to represent your keys. But in no way is there a limitation. You can definitely go further and beyond that by, so let's look at an example on the next slide. So in this we have a comparator. So our relation, which on this slide is defined as less than or equals to, here it's defined as is less than P and Q, which tests whether P is less than Q. So you see this relation is defined as is less. And we can do a lot of different things with this. If suppose we can define the relation. So here we have the operator for the particular relation. We have 2 pointers, P and Q, and all we're doing there is we're getting a value from P, get X, and we're checking if it's less than Q's get X, which is a value from Q. And we're testing this as a representation for the relational symbol. So this is an example of how you can do it with objects. But obviously, if you're just comparing two keys which are integers, you wouldn't need a separate method for it. You could just do it in one line. You can say is 2 less than 3, and then you get a true or false value. Okay, great. So we've got this data structure called the priority queue, and it's got certain methods. But suppose we have this problem. We've got a set of entries, and the entries, it's a collection of entries. Suppose one of the entries, it comes from the class animal. These are objects from the animal class. And suppose one object is dog, and here's the associated key value of 5. We've got another object from the class animal, and it's a mouse that has the associated key value of -1, and another one, cat, which has the associated key value of 10, suppose. You have a lot of these, all right? So you got about 20 different entries, all right? Can we use priority queues to arrange these objects based on their keys from highest to lowest? So if you think about it, you have a priority queue which can collect these objects. You can insert all of these entries into this priority queue, and then you can extract the minimum at a time. So if you remove the minimum from the priority queue, well, then you just have to put it as the first item in any kind of list. It can be an array or a linked list. So you just put it as the first element in the collection. Right, so now you've removed that element from the priority queue. Then you remove the next one. That becomes the second element in the auxiliary data structure. It could be a list or a linked list or an array. Then you remove the next minimum from the priority queue. So you're extracting the minimum one at a time, building an auxiliary data structure. Could be a list, could be an array, but what's actually happening is that the output of that array would be the entries in sorted order from smallest to largest. And the way of doing this is called priority queue sorting. Now, of course, the complexity of the priority queue sorting depends on the complexity of the remove min operation, okay? Because you're doing n remove min operations. So if your remove min operation is also n, then the complexity of your priority queue sorting would be n squared, all right? So n times n, because you have n entries and each remove min is n, so it'll be n times n, which gives us n squared. So that's quite, oh goodness, that is quite problematic, because that's quadratic time. But suppose your remove min was a bit cheaper. Suppose you could achieve 0.1, very unrealistic, but 0.1 for remove min. Then you could actually achieve ON, total complexity, because it would be 1 times n. So you'd see, so my point here is that based on how you implement remove min, the priority queue sorting algorithm, the one that I just described, it differs. So what's important is being computationally savvy while implementing remove min, because if you do this well, or if you arrange your priority queue structure well, then you could actually achieve very good computational savings. So let's try actually to look at two different implementations of a priority queue, and we'll see the different ways you could represent the complexity for remove min based on the actual architecture of our priority queue, and we'll see what will be the computational savings, or what would be the, well, basically just the computational complexity of the priority queue sorting algorithm that we come up with. And this is all depends, all of the pressure depends, comes from the remove min implementation. So we see there's two different ways of representing a priority queue. Well, there's two ways that I'll show you in this lecture, and then in the next one I'll show you a third way, which one might be a bit better. And we'll discuss the trade-off here. So looking at the sequence-based priority queue, so now we're looking at, so sequence-based means that we're representing our entry, our values and objects, so our entries, as a sequence. So connected in this way, like a list or an array, it's a sequence. So you've got, you could implement the priority queue as a unsorted list, okay? Or you could implement the priority queue as a sorted list. Now I want you to pause this video and think about what would be the complexity of insert if you are adding it to a unsorted list, which is the architecture of this priority queue. And what is the complexity of insert if you are adding an entry to a sorted priority queue? So the priority queue needs to always be sorted in this case. Can you see there's two? This is for unsorted lists, this is for sorted lists. So we see that if you have an unsorted list representing a priority queue, then it doesn't matter where you add the entry. You could add it to the front, you could add it to the end, but as long as you can access the front and end in constant time, insert will take 0.1. Okay, so your insert for an unsorted priority queue will be 0.1, because you can insert it anywhere. You could insert it here, you could insert it here, it doesn't matter. But then what would be the remove min? Well, looking at these keys, we would need, because it's unsorted, we would need to find the minimum. And what is the complexity of finding a minimum value or the minimum key in a sequence-based priority queue which is unsorted? Well, we're going to have to visit everything, because we have no guarantee that the minimum will be in any particular position. So we start here. Is this, well, we'll say, well, our current minimum is 4. We then go to the next one. Well, 4 is less than 5, so our minimum is still 4. 4 is greater than 2, so our new minimum is 2. 2 is less than 3, so our minimum remains 2. And then 1 is less than 2, which means our minimum is now 1. So we had to go right through the sequence-based priority queue, unsorted. We had to go right through it, and so we had to visit every entry, and if there's n entries, we would have ON, which would be the complexity of the priority queue. So we have to go to each and every one of them. So we see that the remove min for an unsorted priority queue is ON. That's the complexity of that. Okay, I hope that's clear. Because you have to traverse the entire sequence. That's important. On the other hand, let's now look at the insert and the removement for a sorted priority queue. So in a sorted priority queue, we've still remember the total order relation. We've got our keys arranged in order from 1 to 5. So you got the smallest, then the second smallest, then the third smallest, then the fourth smallest, the fifth smallest, and so on in order. These are our keys. Remember that each of these keys has an associated object, but we've just left it out for just to simplify what we're doing. And the performance here, let's look at insert. Now, before in the unsorted list, we could insert either at the front or the back. It didn't matter. But now it does matter. We have to insert a new entry with the associated key to the correct position. So if we are adding a key 6 here, we would need to find the correct position for 6. If we are adding a 2.5 here, we would have to find the correct position for 2.5. We would have to find the correct position for 4.5 or for -1 and so on. So your keys have to be inserted in the correct position. That's very important. And to find that correct position, you would need ON because you would need to find the correct position. So you would just have to go in, maybe you can start here and you can move to the next one. Suppose we inserting 3.5. Well, it doesn't go here. It doesn't go here. It doesn't, it goes over here. So we'd have to find this position. And because in the worst case, like inserting a 6 or anything greater than 5, we would have to go from the beginning right to the end. So we'd have to traverse all of the entries. Because we have to, in the worst case, to do that, this means the worst case, then the complexity will be ON time. Okay, so that's important. We always look at the worst case in complexity theory because we want to see, we want to be able to gauge what would be the worst scenario. Because that also obviously would take the longest time. In some cases, we might also want to consider the average time complexity, and we would find amortized ways of doing this. But that was the lectures on analysis of algorithms. So then let's look at the removement. So well, this is much easier. This is much easier because now if we have a priority queue represented as a sorted list, we know that the minimum will always be in the beginning. It will always be the first item. So as long as we can access that first item in constant time, we can always achieve the removement in O1. So we see that implementing it with an unsorted list, insert takes O1, removement takes ON. In implementing this with a sorted list, our insert takes ON and the removement takes O1. So now you have to tell me which is better. Should we implement it with an unsorted list or a sorted list? Right, so the most skeptical of you will say, hang on, Ritso, it should be based on the application. And you'd be right, okay, because if you have more inserts than removes, okay, then this makes more sense. If you have more removements than inserts, then this makes sense. So depending on the priority queue, you would depending on the application, because if you look at the computational complexity is very much the same theoretically here. This would now depend on the application. Yeah. So later on we'll find a more efficient way of doing this, and that has to do with a new data structure called heaps, which we'll get to. Right. So. In the previous slide, you saw that you could implement a sequence-based priority queue using an unsorted list or a sorted list. So there's two sorting algorithms that comes about through the implementation of the priority queue based on using an unsorted list or a sorted list. And if you use an unsorted list, you can implement a sorting algorithm called selection sort. And if you use a sorted list to implement a priority queue, you can build a sorting algorithm called insertion sort. And we're going to look at these two algorithms now. So selection sort is a type of sorting algorithm. It's a variation of priority queue sort where the priority queue is implemented with an unsorted sequence. So this is important. It's represented with an unsorted sequence. And the running time of selection sort, well, the idea is very much the same as before. We insert the elements into a priority queue with n insert operations, and because it's unsorted, we can achieve on, right, for all of the entries. And then we remove the elements in sorted order from the priority queue with n remove min operations. Okay, so to remove the first one, well, we would have to search for the entry, and since there's n entries, the first removal will take n, the second removal will take n minus 1, the third removal will take n minus 2, and so on. So the priority queue implemented with an unsorted sequence is decreasing with every removement. So that means that we can't simply say that it's always going to be n. When you remove the first minimum from the set of all entries, you take on. When you remove the second, well, now it's one less in the priority queue, despite it being unsorted. It'll still be n minus 1. Then it'll be n minus 2, n minus 3. And so if there's 2 items, then the remove min will take 2 constant time. And if there's 1 item, it'll be O1. So if we add all of this up, if we add 1 plus 2 plus 3 plus 4 plus 5 plus n minus 3 plus n minus 4 plus all of this n minus 2, n minus 1, and then n. If we add all of that up, we're going to get n squared. If you don't believe me, I will quickly turn your attention to a genius called Friedrich Gauss, and he was a real great genius in mathematics. They say that if we knew what Gauss knew, if he published everything that he knew at the time, we would have advanced in mathematics by 50 years. That is such a great genius. And he was making a lot of noise in his class, and the teacher just couldn't stand him anymore. And she told him, just add the numbers from 1 to 100. And he gave the answer 5,050 in a split second. He did it so quickly. And obviously the teacher didn't recognize his genius, but he just came up with a very powerful way of adding sequences. And they teach this to grade 12 learners, but they don't really give you the history. So let me very quickly show you the analogy. Right. So in order to do this, he said you've got 1, that's the first item. I'm writing with my mouse, so I apologize if it looks very ugly. And you got 2, and then you have 3, so you're adding the numbers from 1 to 100, and you got all the numbers in between. And then you've got 97, 98. This is me drawing with my mouse. 99 and 100. And the way you would do this is you would simply, okay, I think that's done. I can change the color. Oh, it doesn't let me. Okay, it doesn't matter. So so the way Gauss did it was, he actually decided that he discovered that if you add the first number to the last number, you get 101. If you add the second number to the second last number, you get 101. And he saw that you can pair numbers in this way. But how many pairs will you have? Well, you'd have exactly half of the total. So all he did was he multiplied 50 from 50 pairs by the sum of the two key values for the pair, and that gave him the answer 5,050, and that's the answer if you sum 1 to 100. And this is an extraordinarily powerful contribution, because he just discovered how to add these large series, these large expansions very easily. Right, so going back to this, the actual example that I wanted to show you, you could say here, from 1 to n, you can do it in the same way. You say, well, 1 to n, that's n plus 1. And then if you add the next 2 to n minus 1, it gives you n plus 1. 3 to n minus 2 gives you n plus 1. And so on. And how many of these do we have? Exactly half. There's half of these, half of n for the number of pairs. So it becomes n over 2 multiplied by the sum, n plus 1. I'm sorry, it's a bit untidy. I can't help it. I'm drawing with my mouse here. So then if you multiply in the brackets here, you'll get n squared over 2 plus n over 2. And we know from the notes from the analysis of algorithms section of this course that lower order terms and constants don't matter. So we can sketch out the constants, which is this, the half, is 1 over 2 multiplied by n squared. And the 1 over 2 multiplied by n, we can take that out because those are constants. And we say lower order terms too can be taken out. So we scratch out our n. And that gives us n squared. So that's how we get this. So let's look at the next slide. So this slide shows us how selection sort actually works. So the way it works is you're given an input sequence. So here's your input sequence. And you're given a priority queue. This is your priority queue. So this is your sequence. This is your priority queue. So all we've got to do is just insert the elements of the sequence into the priority queue. Remember, that's step 1. Okay, so let's do that. So we insert them. We'll take the first 7 out, put it into the priority queue. Take the 4, put it in the priority queue. Remember that this is unsorted. This is unsorted. So you can just you can simply just put it anywhere. Doesn't matter. But the complexity for each of these is 1. So it's 1. You just edit anywhere, edit anywhere, edit anywhere, and the total complexity here will be O(n). And then what we do is, once we've added all of the sequence, the entries into the priority queue, we then just have to remove the min. So to find the minimum here, this will be n. To find the minimum here, this will be n plus 1. N minus 1. To find the minimum here, it would be n minus 2. To find the minimum here, it would be 2. To find the minimum here, it will be 1. And so then if we So if we add this up, we would get the complexity, as I've shown you here before, in this little spot, you get the complexity O(n) squared. O(n) squared. So the total complexity for selection sort is n plus n squared. And because we remove lower order terms, we just get n squared. So the complexity for the selection sort algorithm is n squared. Great. Let's now look at the insertion sort algorithm. So insertion sort is a variation of priority queue sort, just as we've seen before with selection sort. But this time we implemented with a sorted sequence. And in this case, because we are maintaining a sorted sequence as our priority queue, we need to make sure that every element, every entry that's inserted is put in the correct position. So, we need to now work out the complexity. Well, inserting an item into an empty sorted sequence, what would be the correct position? Well, because it's empty, it'll be the first position. Okay, so we put it in the first position. Inserting an element, an entry, in a sorted sequence, and you want to put now a new element into it, and there's only one element in the sorted sequence, well then where would be the correct position? Well, we would have to just compare it to the first position, and it might even go before or it might go after that item. So that'll be 2. Then if you have 2 items, then you have to do 2 comparisons, and it'll be 3, and so on. If you have n items, then you would have to compare to each of them, which will be n. So we see we're going to be summing from 1 to n, and we know that this is equal to O(n) to find out n squared, to find out what is the sorted sequence, what is it going to be if we have n entries to insert into it. So this is how we get the complexity for inserting into a sorted sequence. And the reason why it's so expensive is because we're maintaining the sorted sequence. We're not just adding anywhere, we're looking for the correct position. So then it brings us to, removing an element from, removing the min or removing the max from a priority queue implemented with a sorted sequence. That is now much easier. Well, if we're removing the minimum, we know it's the first element because it's sorted. If we're removing the maximum, we know it's the last element because it's sorted. So all we have to do is just be able to dereference the first and last index, depending on whether we want to remove the min or the max, and then do it. Remove the min or remove the max. And if we remove the min from a sorted sequence, it becomes O(1). Remove the next min, O(1). Remove the next min, O(1), and so on and so on. So if you do n O(1)s, you're doing O(n). And that's how we get this complexity. But in total, the complexity of insertion sort will be the complexity of the insert, which is n squared, plus the complexity of the remove, which will be O(n). So it'll be n squared plus n. which gives us, if your asymptotic complexity gives us O(n) squared, because the lower order term would fall away. So that gives us the total complexity of O(n) squared for insertion sort. Let's look at an example. Well, before in the selection sort, this here wasn't sorted. Okay, we would just have an unsorted list, but now we've got to maintain. It needs to be sorted. So what are we doing? Well, here's our sequence that we're entering into our priority queue. We need to do it one by one. We start off with the 7. Well, any position here would be, so the complexity here is 1. Then we have to put the 4 in, so we compare it to 7. The 4 goes here. That takes a complexity of 2, because we need to do 2 comparisons. And then you need to put the next one in, then you get 3. The next one in, you get 4, all the way to n minus 1 and n. So then you add this up using Gauss's formula, and you're going to get n squared. And then, of course, removing from a sorted sequence, you have a look at this, it's sorted. So where would be the minimum? Well, it's right in the beginning, because it's sorted. So we remove the minimum, get the next item. Then we remove the next minimum, we get the next item, and so on and so on. That's how we could end up with a sorted sequence at the end. So this is how we could perform insertion sort. So we just see it's reversed, and this is the beauty of having a priority queue implemented with a different architecture. You get different computational performance based on it. And remember, the time complexity matters more here than the space complexity, because the space complexity is still n no matter what. No matter which algorithm you're using here, whether it's insertion sort or selection sort, your space complexity is constant, it's O(n). But the time complexity differs. The time to run this algorithm differs based on which segment we're in. We inserting into a sorted sequence, or whether we're taking it out of the sorted sequence. And that's what matters. So that's important to remember. The last thing I'd like to show you is how to perform in place insertion. So we say that an algorithm is in place if it uses the same, if it manages all of its computation within the same space that the problem is presented in. Then we say it's in place. So we have the problem here of we're trying to sort the sequence, and all we're doing is we're keeping track of 2 arrays inside of this larger array. So we're using the same space. That's why we call it in place. It's in the same place. This is the sequence. We're trying to sort it. Well, all we got to do is we've got to put 5 in the correct position. We put it in the correct position. Then we've got to put 4 in the correct position. So this 4 exists in this list, and we've got to put it in the correct position in this list. So we take 4 and put it in the correct position. Now we've got this sublist and this sublist. We now need to put 2 in the correct position. So we put it in the correct position. And then we have this sublist and this sublist. Do you see no additional storage is needed? We're doing everything in the same place. We now need to put 3 in the correct position. We got this list and this. We're going to need to put 1 in the correct position. We're going to put it in the correct position, and then we can then just output this as the list in sorted order. And this is how we can do this with insertion sorts. Now, the beauty of this is that swaps are cheap to do. Swapping to integers, because remember, you're just changing the position of them. It's 3 steps, right? You say temp is equal to this one, temp 2 is equal to that one, and temp 1 is equal to temp 2, or whatever the case might be. And that's how you can swap your variables. You can swap your different integers. But what's important here, the reason why I'm showing you this is because you can perform insertion sort in place. There's no, you don't have to do it the way we've done it here, where you have a separate priority queue, additional data structure, and then the sequence array, which it's presented in. So here you've got 2n. The space complexity is 2n, because you've got n space for this array, yeah, and you've got n place for this array. So n plus n is 2n. So that's the space complexity. But remember, you don't need to do it that way. You can do it this way, and this only is not 2n. This is just n. Space complexity. There's a difference between time and space complexity. So yeah, so if you're struggling to understand the difference, please go to the previous section on analysis of algorithms. Okay, great. In the next lecture, we'll look at how to implement priority queues using heaps. So I'll see you there.